Okay, how's it, Chase? Today we're going to be looking at section 3.13. My pen is set to black. Lovely. Let me just sort that out quickly. Okay, and we're back. Okay, so today we're going to be talking about complex equations, which is section 3.13. Just like this pen is still in black. Okay, section 3.13, which is complex equations. Okay, now complex equations are quite interesting because basically we can break the equation up into a real and an imaginary part. So if we have one complex equation, we end up with two equations. So for example, the book gives the example, let's see, x plus y plus j x minus y is equal to 7 plus 3j, right? So from this, when it comes to complex equations, the real part of the left-hand side, which is this piece over here, and the real part of the right-hand side must be equal, and the imaginary part must be equal to the imaginary part. Okay, so we can actually get two equations from this. So now what we're going to end up with is from the real parts, so the real parts, we're going to have x plus y equals 7, and from the imaginary parts we're going to have x minus y is equal to 3. And then we can solve it like a normal set of simultaneous equations, and we will have our solution to the complex equation. Quite simple. So let's quickly do that. We've got okay, so from equation 1, x plus y equals 7, therefore x is equal to 7 minus y. Then we can substitute x into the second equation here, and we end up with 7 minus y equals 3. So we've got 7 minus 2y equals 3. Minus 2y is equal to, take the 7 across, it becomes negative, so we've got 3 minus 7, which is negative 4. Therefore y equals 2. And then we can solve the then we can substitute y equals 2 into either one of these two equations and solve for x. So I'm going to choose this one, this equation right here. X minus y equals 3. We substitute y equals 2. X minus 2 equals 3. Therefore x equals 5. Okay? And as with any simultaneous equation, if we sub 5 and 2 into either one of these two equations, but let's use the first one. If we sub 5 in for x and 2 in for y, you'll see that that is equal to 7. So the left-hand side equals the right-hand side, so we've obviously solved our equation now. Okay, so let's just do one more example that your book has on this. This one looks like a bit of a longer one, so let's get cracking with it. Okay, so the example is j, no, sorry, shouldn't be a capital J, j plus 1 squared plus 2 plus j times j is equal to x plus y plus 4yj. Okay, now we can't start off with this equation by simplifying it into like separating the real and imaginary parts right away, because you see we've got real and imaginary parts inside these squares, and so these brackets are going to result in real numbers and imaginary numbers. So the first thing we need to do is to simplify this a little bit by multiplying it out so that we can get it into the general form, which is a plus jb, right? So when we've got squares and j squared and so on, we can't just separate into real and imaginary. We need to first simplify the equation. So let's start by simplifying. Okay, so let's start here. J plus 1 squared is equal to j squared plus 2j plus 1, and I just did that by FOIL. Okay, then we've got plus 2 plus j times j, so that gives us, multiply the j in as you would a variable, 2j plus j squared is equal to, this right hand side doesn't need simplification. You can see there's real parts over here, and then you've got your imaginary parts over there. Okay, so right hand side is just x plus y plus 4yj. There we go. Now let's just continue to simplify this, because we've still got squares here and we need to get rid of those. So j squared is minus 1 plus 2j plus 1 plus 2j, and j squared is minus 1. Okay, and keep our right hand side, x plus y plus 4yj. Okay, this left side still needs a bit of simplifying because we can add things and subtract things. So negative 1 plus 1 cancels. 2j plus 2j is 4j, and we've also got this minus 1. So we've got minus 1 plus 4j. J is equal to x plus y plus 4yj. Okay, now the left hand side and the right hand side are in the standard form over here. And let me show you that. So I'm going to show you the real and the imaginary parts here. You see that we've got real, then we've got imaginary, then we've got real, wrong color, real, and then we've got imaginary. Okay? So the x and y are real numbers because they don't have a j in front of them. So they're just variables. Okay, so now what do we do with complex equations once they're simplified? Then we can split into a real and a real equation and an imaginary equation. So let's do that. Let's start with the real equation. The real part of the equation is, what's the real stuff on the left? Minus 1 is equal to real stuff on the right, x plus y. Okay, then let's do the imaginary part of the equation, which is, okay, so the imaginary is 4j is equal to 4, when you're doing the imaginary parts of the equation, it's not necessary to include the j's. You can drop the j's because what happens is they'll cancel anyway. So the imaginary part is just 4 is equal to 4y. Okay? And there you go. Now this is easy to solve. You've got two equations. You need to solve for two variables. Let's start off with this equation over here, equation 2. Okay? Or the imaginary equation. If 4 equals 4y, then y equals 4 over 4, y is equal to 1. Then we can substitute 1 into that equation for y, and we get minus 1 is equal to x plus 1. Okay? Therefore, x equals minus 2. Okay? And that's it. We've solved the complex equation for x and y. Quite a nice example. And let me just check that the answer is right with your book. Yeah, now it is. Okay. So we've solved for x and y. 100%. Alright. Okay, let's move on to the next section. I just want to open a clean page for us. Okay. So, before I move on, let me just do a summary. So, complex equations there's 2 steps. Three steps actually. First step is simplify. And by simplify, I mean multiply out all brackets. Okay, and then the second step is separate into 2 equations, i.e. a real and an imaginary equation. Okay? Then, number 3 is solve the 2 equations simultaneously. So in the normal way that you would solve a set of simultaneous equations, you continue and you just solve for x and y, and then you will have solved the complex equation. Okay, now that we've done with that, we can move on to the next section. Okay, so the next section in your book is section 3.14, which to me, I'm not sure why, sorry, that's my phone. Section 3.14, I'm not sure why it's at this point in your book, but anyhow, we're going to do it. The section is application of complex numbers. According to my phone, I'm quite popular. Okay, let me just silence that before it interrupts us anymore. Alright, so what they're trying to do here is show you how you can use essentially actually the Cartesian plane and trig in order to add forces. And okay, then they go on to some other stuff, but this is more science and trig than what it is really complex numbers. So I'm going to go through the first example, which is example 38. I'll do that quite quickly because it's actually quite simple. I think it's something you'll understand quite nicely. So it says calculate the resultant of forces acting on a point. And they give three forces, okay? A is 200 newtons at 32 degrees. Then we've got B is 50 newton at 119 degrees. And C is 80 newtons at 224 degrees. Okay, so the easiest thing to do when you're calculating the resultant of forces acting on a point is to draw your Cartesian plane and work from there. Okay, so let's draw it. We've got, I'm going to do these in color, okay? We've got the red one, the green one, and the blue one. Okay, so 200 newtons at 32 degrees is force A. Oops, wrong color. Okay, there we go. That's 200 newtons at 32 degrees. 32 degrees, and 200 newtons. Okay. Then next, we've got 50 newtons at 119 degrees, which is somewhere more or less here. Okay, 50 at 119 degrees, and remember your degrees are always measured counterclockwise from positive x-axis unless otherwise stated. So this is 119 degrees. Okay, and then we've got 80 newtons at 224 degrees, which is round about here somewhere. 224 degrees. So once again we measure it like that. Okay, that's 224 degrees, and the force is 80 newtons. You should actually be drawing the lengths of these arrows more or less to scale. Mine aren't quite, but obviously the larger the force, the longer the arrow should be. So the application of this is we can find the resultant by breaking it up into X and Y components. I see they do it in a very strange way in your book, and to be perfectly honest, I don't see how it's necessary. So I'm going to show you how to do it my way and the way that it's done in all science courses. Okay, so this is your x-axis and this is your y-axis. You could call it your real and imaginary axis if you really wanted to, but to be quite frank, that's just it's pointless. Okay, so if we look at this red force here, you can see that it's got an x component and a y component. Okay, how are we going to find out what the x and y? Actually, now that I think of it, this is actually quite interesting the way they do it. Okay, let's try it the way they do it. Let me show you what they're talking about. Okay, so let's track back. Let's call it our real and imaginary axis. Okay, and let's express these three forces in polar form. So the sum of the forces that we have here, okay, the sum of the forces is equal to, the first force is 200 angle 32 degrees, and it's at a, this is the sum of the forces in the x direction, or in the real direction. You see, because we're measuring our angles from the real axis. Okay, so the x direction or the real direction. Okay, so we've got 200 angle 32. We've also got, so plus 50 angle 119 degrees, and we've got plus 80 angle 224 degrees. Okay, now we can break this up into real and imaginary components using so remember the general form, A plus JB. So we do that for each one of these polar form equations. So let's quickly do that. Yes, we need to break it up into polar form. Right, so let's quickly break up each one of these into rectangular form, sorry. So we know that A is equal to R cos theta, and B is equal to R sine theta. Okay, now you can calculate all of these manually. What I'm going to do is I'm just going to pop it into my calculator and convert it all to rectangular form for you. So let's start with the first one. The first one is 200 angle 32 degrees, which is equal to 169.61 plus J 105.98. Okay, then we do the second force. So 50 angle 119, 50 angle 119 converted to polar form gives, convert to rectangular form, sorry. That gives us negative 24.24 plus J 43.7,73. Okay, and then let's quickly do the last force. Pop that into the calculator, so that gives us plus 80 angle 224 is equal to negative 57.5 minus 55.6, and that's J 55.6, sorry. Okay, now that we've got that, we just add our real and imaginary components. So we're going to add 169 minus 24 minus 57, and then we're going to have 105.98. So plus J 105.98 plus J 43.73 and minus J 55.6. So we add the real and imaginary parts separately as we normally would, and that leaves us with 87.9 plus J 94.12. Okay, so now we've got this is now our resultant. We've found our resultant. So on our Cartesian or our imaginary plane, okay, real, imaginary, okay, this force lies somewhere here. The real part is 87, the imaginary part is 94, so here is our resultant force. Lies right over there. Okay, but we don't know the length of this arrow. We know the x and y coordinates. So how do we get the length of that arrow and the angle? Because that's what we want. So how do we do it? We convert this back to polar form. Okay, and we know that polar form is in the format z is equal to r angle theta, right? And r is the square root of a squared plus b squared. Theta is arctan b over a. Okay, and then we just pop the numbers in there. So r equals square root of 87,9 squared plus 94,12 squared, and theta equals tan inverse of b, which is 94,12 over a, which is 87,9, and then we find that r is equal to, let's just pop it in there, r is equal to 128,8, and theta is equal, now remember we're working with forces, so that's newtons, and the angle is 47 degrees. Okay, and there you have it. So now we can just write it in polar form. The resultant force is equal to 128,8, angle 47 degrees, and that's newtons. And there you go. Okay, I'm just going to pause the video and take a look at this next example so that I can figure out what exactly they're doing there. Okay, I'm actually going to leave the lesson there, and then I'm going to quickly make another video a little bit later on this last example and maybe a few of the exercise problems. Yeah, I've just got to get going now, so I can't continue. But yeah, I'll make another little video on the last example problem and some of the exercises, and yeah, then I'll see you next week again. Cool. Cheers.